Hello. In my last video about trigonometry, we talked about modern spherical trigonometry as it's been practiced for the last few hundred years. In this one, I'm going back to the origins of the subject 2000 years ago. And the reason I'm doing them in that ahistorical order is because modern spherical trigonometry is relatively easy to get your head around, relatively approachable, whereas the ancient stuff's somewhat more complicated. And so in some sense, I'm using the modern spherical trigonometry as a gateway to the ancient. So if you haven't watched that earlier video, you might want to do that before watching this one. So I mentioned several times, I think, that trigonometry was invented by astronomers and used only by astronomers for 1,000 years or so. And what were they studying? Well, this sphere, the celestial sphere. And so they were doing spherical trigonometry right from the beginning. So spherical trigonometry is pretty much as old as trigonometry itself. So let's look at the origins of all this. So the earliest geometry that's relevant was done by the Babylonians some 4,000 years ago. When we get to the ancient Greeks, Pythagoras and Euclid, who got some of their ideas from the Babylonians, none of them had trigonometry. The earliest trig table we know about is Hipparchus, just before the turn of the millennium. But all his works have been lost, so we don't really know much detail about that. The earliest tables that survive are those of Ptolemy of Alexandria, and he told us a lot about how he calculated and all sorts. And he was definitely doing spherical trigonometry. The earliest write-up of spherical trigonometry is from Menelaus. So he's a little bit older than Ptolemy. So Ptolemy was using Menelaus's methods. It would be a mistake to think that Menelaus invented all the spherical trigonometry that he wrote up, just as Euclid didn't invent what he wrote up. Euclid collected all the geometry that was known in his time and added some proofs and put them in a logical order and created a sort of coherent whole out of them all. And Menelaus did much the same thing on a much smaller scale, of course, for spherical trigonometry. So his methods of use of doing spherical trigonometry were probably what Hipparchus was using a couple of hundred years earlier, but we can't really know that. So let's recap some of the stuff we established in the first video about spherical geometry to start with. So we use great circles that play the roles of lines, and great circle arcs play the roles of line segments, but we measure them as angles, angles subtended at the center of the sphere, which means we don't ever need to worry about the radius of the sphere we're talking about. So 2 points determine a great circle, unless they're polar opposites. Two great circles determine two polar opposite points. So it's a bit like Euclidean geometry, but just not quite. One difference is that a closed curve doesn't have an inside and an outside on the sphere, as it does in the plane, but it does divide the sphere into two regions. But actually, we're not really going to use that in this video. Moving on to modern trigonometry in spherical triangles. So it is about triangles. So we use the same notation we use in the plane. So we have capital A, B, C as both the names of the points of the triangle, the vertices of the triangle, and the angles. And we call these surface angles, these angles on the surface of the sphere. The sides of the triangles, that's great circle arcs, and they're measured as angles subtended at the center. So these angles here correspond to the arcs. So a spherical triangle is associated with 6 angles. And armed with that notation, we end up with the spherical sine rule and the spherical cosine rule, which are the core of modern spherical trigonometry. But none of that would have made any sense to Menelaus or any of his astronomers of that sort of period. And for a particular reason, they didn't measure surface angles. So they measured the angular separation between two stars. So that's an arc, essentially. But they didn't measure angles on the celestial sphere, which would involve looking at 3 stars. And sort of, they didn't care about it. They didn't measure angles like that. They weren't interested in working them out. And so none of their formulae had those angles in them. They only had arc lengths. Now, it is possible to express a surface angle as an arc length. So this surface angle here between these two great circles is also this angle here between the two planes of those great circles. And so it corresponds to this arc here, this arc length. So a surface angle corresponds to an arc length quite a long way away. But at any rate, the ancient astronomers used only arc lengths in their formulae. So Menelaus of Alexandria, he's the hero of this video, really. So he's called of Alexandria, because he was probably born there, but he did his famous work in Rome, and other Roman authors knew him and mentioned him. So he's fairly well documented. So Alexandria, of course, was a Greek city in the Roman Empire, and it's when nowadays what we call Egypt. A lot of the ancient Greek mathematics was actually done in Alexandria. So it was done in Greek, but not in Greece, or not what we would nowadays call Greece anyway. So he wrote quite a lot, but only one book survived, and that's fortunately for us the one called Spherica, which is about spheres. So he was probably the first to recognize great circles as the analog of straight lines, and he defined spherical triangles just as we have done. So he sort of drew out the analogy between spherical geometry and plane geometry. Now, if you look up Menelaus's theorem on the web, you'll almost certainly find what I'm calling Menelaus's plane theorem. It's a theorem in plane geometry. And Menelaus quoted that. He didn't prove it, so it's quite wrong to call it Menelaus's theorem. He did prove Menelaus's spherical theorem based on the plane theorem. But as I've suggested earlier, I don't think he was the first person to come up with that theorem. But that theorem became the mainstay of astronomical calculations for a millennium or so. So let's have a look at this theorem. So we start with the plane theorem. So it concerns this configuration here of four lines, or line segments rather, and it says AF over FB equals AE over EC times CD over DB. Now, that's quite complicated and difficult to remember, and you could probably tell I can't remember it. So I had to crib from this. And the ancients complained that it was difficult to remember too, but they still used it. There is, in fact, a modern version of it that's easier to remember. So if we think about a particular triangle in this configuration that I've called ABC, then there's a fourth line involved that isn't a side of that triangle. And what we do is we navigate round triangle ABC, and on our way from A to B, we visit the point where the fourth line meets that line. So we go AF over FB, and then we carry on BD over DC, CE over EA. Now, these are vectors, they're signed line segments, if you like. So these ratios can be negative. And in fact, the first one isn't it? So AF over FB, that's a negative one. The other two are positive, BD over DC, CE over EA. So two of these are positive and one negative. So we can tell without doing any further work that the product of them is negative. And what the theorem says that it is in fact -1. And then actually in this configuration, there are other triangles. So this triangle, and exactly the same thing happens in triangle AFE. We do AB over BF, FD over DE, EC over CA, and that last one is the one that's negative this time. And again, the theorem says that the product is -1. And then there's some other triangles, this little one here. Now, this time, the fourth line doesn't intersect this triangle, but never mind, the theorem's still true. So let's see that we're doing this in triangle DCE. So we go DB over BE, CA over AE, EF over FD. And this time, all three of those ratios are negative. So we know the product is negative, and the theorem says they're in fact -1. And there's another triangle there, and that looks just the same. So for Menelaus, this is actually two theorems. This one where the fourth line intersects the triangle in question, and this one where it doesn't. But for us, it's one. These theorems here are interesting. What we're doing here is comparing lengths along one line. So we never compare lengths in different directions. And that tells us that this isn't really a theorem in Euclidean geometry. In category theory terms, this is a vector space theorem. It's not a Hilbert space theorem, which in turn suggests that there might be a nice A-level style vectors proof of this result, and there is. So I'm going to show two proofs, one of the sort that Menelaus or even Euclid might have done, and a modern vectors proof. So let's do an ancient proof. So what we start with is a construction, that one. So we put this line segment here parallel to that one. And now we've got lots of similar triangles. So if we look at these two triangles, that big one is similar to that one. And so we can say AE over GE equals AF over BF. And then these two triangles are similar. That's AFD and CGB. And we get the same sort of thing. EC over GE is DC over BD. And if you combine all those together, you get from this one, AF over BF equals AE over GE, which is AE over EC times EC over GE, just putting in that couple of copies of EC, and then you apply this one to that, and you get that, which is Menelaus' theorem. So it's not very deep. Now let's look at a modern vectors proof. So this time I've drawn not just the line segments, but the whole lines, because sort of that's the way vectors proofs work, isn't it? So I'm going to set an origin at C, so C is going to be O as well. Now, and I've got added two vectors. This one is A and this one is B. OE is some multiple of OA, and I'm going to call it mu, so that's mu A. OD is some multiple of OB, and I'm going to call it 1 minus lambda, just because the algebra works out nicely. So OD is 1 minus lambda times B. Now, F. On the one hand, it's on this line. So it's a mixture of A and B, if you like. So for some nu, it's nu B plus 1 minus nu times A. And on the other hand, it's also on this line. And so it's some mixture of OE and OD. And so the sum alpha for which OF is alpha times OD plus 1 minus alpha times OE. Now we just have to mix all that up in the big algebra mixing pot. So I seem to have turned this equation around for some reason. So OF is this bit from there. And that's it. So alpha OD is alpha times that. That's there. And 1 minus alpha times OE is 1 minus alpha times that. And then we collect the A, B terms and we get that. And now we're in the familiar situation of having a multiple of A equal to a multiple of B. And the only time that can happen is if both multiples are 0. So we set those two. We've got two simultaneous equations. We eliminate alpha from them and end up with that. You can pause the video and check my algebra if you like. I think it's right. So that works out to mean that. Then we look at the product that occurs in Menelaus' theorem, and it turns out to be that, which is -1. So there we go. As I say, pause the video if you want to check my algebra. Now we want to move on to the spherical theorem. And to do that, we need a stepping stone theorem. And here it is. So we have an isosceles triangle, and we have a line joining this point to the bottom somewhere, I'm not aware, and these two angles, alpha and beta. Now, the little theorem we want to start with is this one. So AD over DB, whoops, come back. AD over DB, it asserts, is equal to sine beta over sine alpha. So let's have a look at that. So if we drop the perpendicular, these two triangles, CAD and CDE, have the same height, namely this perpendicular length. And so the ratio of the areas of those two triangles is equal to the ratio of their bases, which is AD over DB. But also, these two triangles have the same leg length. So this leg of this triangle is equal to that leg of this triangle, and the one in between is common, so it's definitely the same length in both. So this area here is a half that times sine beta, and this one is a half that times sine alpha. So the ratio of the areas is sine beta over sine alpha. So that's our little theorem. Now, just to finish it off, we now get rid of that diet. We get rid of the perpendicular and put in this giant circle and project D onto it. So now look what's happened. So sine beta, so this AD dash thing is an arc and it's measured an angle, and the angle in question is beta. And similarly, this is alpha. And so we can rephrase this as AD over DB is sine of AD dashed over sine of D dashed B. And actually, that's true even if D is outside the triangle. Still works. So that's what we need to prove Menelaus' spherical theorem. So now let's do that. So here we have a sphere with 3 points on it, A, B, C. So first thing we do is construct the plane that contains ABC and draw a Menelaus configuration. So we draw the triangle ABC. Whoops. We draw the triangle ABC, and we put a fourth line in this plane, and we have a Menelaus configuration. So these solid bits are where this configuration comes outside the sphere, and the dotted bits, of course, are inside the sphere. Right. So in that configuration, Menelaus' plane theorem is true. So we have that. Right, let's get rid of the plane. It's cluttering it up a bit. Now, let's use our stepping stone theorem several times over. So in this little plane here, OAC, we can see where it intersects the sphere in this arc, and then we can apply that theorem, that stepping stone theorem, and we get CD over dA equals sine of CD dashed over sine of D dashed A. Then we do the same again here, and we get that sine of BE over EC is sine of BE dash sine of E dash C. And one more time, we do this one. This time, this is where our point is outside the triangle, but the theorem I said is still true. And so we get AF over FB is sine of AF dashed over sine of F dashed B, and this is the negative one. But anyway, so now if we substitute those things into this equation, we get that. And that's Menelaus' spherical theorem. So now there's one more arc we haven't used yet. That's the one on the fourth side. We'll put all the other arcs back in and get rid of the plane configuration. So now that is a Menelaus spherical configuration. So that's entirely drawn on the surface of the sphere. And that's the theorem that applies to that configuration. So that's Menelaus' spherical theorem. Right. So now the next question is, what calculations were Menelaus and his successors making with this spherical theorem? What were they using it for? Well, it turns out that if you look out at the celestial sphere, there are three natural sets of spherical polar coordinates that you might want to use. And they did. So it might surprise you that three-dimensional spherical polar coordinates go back 2,000 years, whereas plain old two-dimensional Cartesian coordinates, we had to wait 1,500 years for them. So what are these three? Well, there's one based on the celestial equator. So the celestial equator is our Earth's equator spread out into space. And so that marks a great circle on the celestial sphere. And the celestial poles correspond to this equator. And famously, the north one is near the star called Polaris, or the pole star. And the spherical polar coordinates have rather odd names. Right ascension, it says eastward from the spring equinox. Now, what does that mean? So we normally think of the spring equinox as a date, or even a date and a time, if we're being more precise. But it's also a point on the celestial sphere. So what the astronomers were doing a lot of the time was tracking the sun's movement against the stars. Now that's quite tricky because you can't see them both at the same time. But of course, the stars are still there with the sun shining. So you can work out where the sun is relative to the stars on the celestial sphere. And it moves over the course of a year around a great circle called the ecliptic. But anyway, so right ascension is measured eastwards from the spring equinox, and declination is the one that's northwards from the equator. Then we have the ecliptic coordinates. So this time, the ecliptic is as it were, our equator, and the ecliptic poles are things 90 degrees away, and the North Pole is somewhere in the Cat's Eye Nebula. And these coordinates are called ecliptic longitude and ecliptic latitude. And then finally, where you're standing, you have your own personal set of spherical polar coordinates based on your own horizon and the zenith, which is the point directly overhead. And the coordinates there are called altitude, upwards from the horizon, and azimuth, eastwards from the north point on your horizon. And it turns out that astronomers spent a lot of time converting between one of these coordinate systems and another. So let's see how that works. So here's the celestial sphere. And this is the equator, and this is the ecliptic. So the sun, over the course of a year, moves around this. That's the celestial North Sphere. Um, and this angle here, we know this angle is well, this arc length is an angle. It's the tilt of the Earth's axis, so we know that's a constant. So let's suppose that we know lambda, which essentially means the date, or the date and the time, if we're being more precise, of where the sun's got to on its journey around the ecliptic. And let's suppose we want to know alpha and delta, which are the coordinates relative to the celestial equator. So the thing about Menelaus's configuration is it's quite complicated. The theorem's got 6 quantities in it. In fact, it was often called the law, the rule of 6 quantities, which means that you need to know 5 of them if you're going to be able to calculate anything else. So, and what that in turn means is that you end up drawing configurations that have a lot of right angles in them. So, and that's what's going on here. So we have a lot of right angles in this picture. So ES, that arc, is a right angle because that's from spring equinox to the summer solstice. EC, similarly around the equator, that's 90 degrees. And similarly, these ones here, these sort of celestial meridians run from the pole to the equator, so they're 90 degrees as well. And that enables us to use Menelaus's theorem on in this configuration. So starting with triangle NXS, I'm going to use the modern version because I can remember it. So this is NXS, and this is the 4th line, which this time doesn't intersect it. So we're going to use the version in which all 3 ratios are negative. And we end up with sine of NB over sine of BX equals sine of XE over sine of ES times sine of SC over sine of CN, and that's going to be -1. Well, it turns out we know most of these things, so we can substitute what we know in there. And again, I'm doing this in a modern way. So SC is minus epsilon, so on. Anyway, okay, work all that out, and it turns out that you can work out sine of delta is sine of lambda sine of epsilon. So that's a theorem that was used a lot over and over again in ancient astronomy. And then the other one, we use triangle XBE. So again, it's one where the 4th line, that's this one, doesn't intersect our triangle. So we go XN over NB, BC over CE, ES over SX. And the ratio of those, product of those ratios is going to be -1. And that's what we get there. And so there we are, we can work out alpha. Now, I've written this as all in signs. You might want to call this one cos of alpha, but the ancients didn't use cosines. Actually, if you may remember, they didn't actually use sines either. They used a thing called chord, which is equivalent to sine, but roughly speaking, it's sine. But they didn't use cosines. They only had one trig table, and that was of the chord function, which is essentially the sine function. Right. There is, in fact, another way to make those calculations using this device, an armillary sphere. And essentially what you do there is you measure it. So you can set up lambda on this thing and measure alpha and delta. But of course, you can't do that terribly accurately. And they were working to great accuracy. If you want to predict the date and time of a lunar eclipse, then you'd better be working fairly accurately. Anyway, so this thing goes back to several hundred years BC. So that's how things stood for 1,000 years or so. Lots of people making lots of very ugly calculations. And then there was a great flowering of intellectual activity around the turn of the millennium, around the turn of the 11th century, in the Abbasid Caliphate, centered in Baghdad, where where intellectuals gathered from all over the Caliphate, where knowledge was gathered from ancient Greece, ancient India, all translated into Arabic and built upon. So an awful lot happened there, not by no means not just in mathematics, but in our particular sphere. So these are 3 of the people who were, amongst other things, astronomers, and some of their ideas. So in the first video, we mentioned 10 right-angled triangle equations, which are associated with Napier, but they go much further back to this sort of period. And the spherical sine rule was definitely discovered around here, as was possibly the spherical cosine rule. You may recall that the history of the plane cosine rule was a bit checkered. So is the spherical cosine rule. And these guys are astronomers, not mathematicians. So they don't really quote a theorem when they're doing their calculations. They just do the calculation. And it's sometimes not entirely clear why they're making their particular calculation. So anyway, it looks as though they're doing something a bit like the spherical cosine rule sometimes, but not much, because astronomers don't measure surface angles, and all these things have surface angles. So these ideas didn't actually really catch on. But the first time we get spherical trigonometry coming down to earth, as it were, is calculation of the Qibla. So the Qibla is the direction you should face towards Mecca when you pray. And knowing where that is an important problem to solve. It turns out Mecca's in the tropics, only just, but it is in the tropics. So there's a cute way to do this, which is to stick a stick in the ground where you are, a vertical stick, and wait until the sun is overhead in Mecca. And you can work that out if you know the difference between Mecca's longitude and your own longitude. So you wait until the sun is directly overhead in Mecca, which will happen at a particular time on a particular day of the year. And you look at the shadow where the vertical stick is, and it's pointing away from Mecca. That's quite cute. At least it is if you're in the same hemisphere as Mecca. If you're less than 90 degrees away. And everybody was at this time, so that's all right. It's not frightfully accurate, I suppose, but it's obviously accurate enough to know which way to face. But or if you want a more accurate version, you'd ask an astronomer. Who else would you ask? Right. So and so this became spherical trigonometry's first terrestrial use. So the point at which astronomers realized that the Earth was a sphere, and you could apply spherical trigonometry to it. So formally, it's the same problem as navigation, really. So let's look at that. This is navigation from A to B, but it's also finding the Qibla. If this is where you are and this is Mecca, so this angle here at the North Pole is the difference between our longitudes. This is 90 minus my latitude. That's 90 minus Mecca's latitude. And so it's just the same thing as we saw in the modern video. Use the spherical cosine rule to discover Z, which is the distance to Mecca, and the spherical sine rule to discover basically the bearing. So that's actually quite simple. But it jolly well isn't simple using Menelaus' theorem. I'm not going to go through the mathematics. It's just too horrible and complicated. I'm just going to show you the diagram. So this is the diagram that was used. And wow. This is about finding the Qibla if you're standing in Ghazni, which is in modern day Afghanistan, and there's Mecca. So the construction you need, there's the triangle we had for the modern version. So we have these two meridians. We need the celestial equator, or the equator, if you like. So, I mean, the astronomers were thinking about celestial equator rather than, and these are thinking of celestial meridians. But anyway, we can think of it as on the surface of the Earth. You need the equator. And of course, this angle is what you want, but they didn't do surface angles. So what they wanted was the arc on their horizon at Ghazni. So this green circle is the horizon, and we want the angle round the horizon from the north point on the horizon round to where our great circle towards Mecca intercepts it. And then it turns out you also need this line, which is the great circle from the west point across to my meridian. And then you do the most horrendous calculation involving, I think, 4 copies of Menelaus' theorem. So it's really hard work. So this guy was another one of those polymaths, and he was really the greatest of them all. He was sort of everything. He was a mathematician, astronomer, and a historian, and a natural scientist. And he was the first person to study comparative religion. He was the first person to sort of look seriously at the history of India, or the Indosphere, I suppose. And he gave 4 methods of calculating the Qibla based on that diagram. And the reason I use Ghazni in that diagram is because that's what he used. Right. This guy, 300 years later, he calculated the Qibla for every degree of latitude and every longitude in the Islamic world. Wow. And just think about the work involved in that. But I don't know how he did it, actually. I don't know the calculator, but I wouldn't be surprised if he was still using Menelaus' theorem. So what happened next? Well, I've called this early European Renaissance. It's not entirely European, but of course, many people were involved in bringing all this great flowering of learning in Baghdad, or centered in Baghdad, into Europe. So I just draw attention to a couple of them. Adelard of Bath, a widely travelled man and a linguist, and he did a lot of translation from Arabic into Latin, and he was in fact including Euclid's Elements. So his was the first Latin version of Euclid to arrive in. So it had travelled from ancient Greece to ancient India and through to Baghdad, and of course into southern Spain, and eventually got into Latin. And Adelard was the first person to make that translation. So that was one thing that happened. This guy here, he was the first person who wrote about trigonometry as a part of mathematics rather than just as a tool of astronomy. And that unleashed trigonometry so that the rest of the world could take note and start using it even when they weren't doing astronomy. And he certainly influenced Copernicus. Well, it says possibly, there's pretty certain actually, and other people as well. So that was the beginning of modern spherical trigonometry. Well, modern geometry. Well, modern mathematics really all started with this movement of knowledge from the Abbasid Caliphate into Europe. So there we are. That's the history I wanted to tell. I hope you enjoyed it.